Okay, so we're gonna move on from a nucleophilicity to a basicity. But first thing first, that's what you need to know that the nucleophilicity and basicity are totally different property. Okay, they are property, but they're totally different thing. Here's the reason why. When you talk about nucleophilicity, strong, weak nucleophile, we look at the rate, right? Strong nucleophile, rate go quickly. Weak nucleophile, rate go slowly. That's a kinetic property. But basicity is a thermodynamic property. What do we mean by that? Here's the meaning of it. When we talk about basicity, we talk about the position of equilibrium. Does it go to the right? Does it go to the left? We don't know how fast they go. They could take like a second or up to 3,000 years, right, to reach equilibrium. But at equilibrium, we know how much the product or reactant will get. Right, so basicity is a thermodynamic property, and a nucleophilicity is a kinetic property. They don't go hand in hand. They don't always go together, or sometimes they're just opposite. Right? Give you some example down here. These guys are troublesome. They are strong nucleophile and also a strong base. They can do both SN1, SN2, E1, and E2. No, I said wrong. They can do both substitution and elimination. Right? SN2 and E2. This guy kind of trouble, but anyway, so they all are strong nucleophile and a strong base. Okay, down here, these iodide, bromide, chloride, sulfide, they are just strong nucleophile. You know, high polarized stability, got charge, strong nucleophile. But they are terrible base. They are weak, very weak bases. Right. On the other hand, so this guy you have seen before, so this guy not nucleophile, right? Too small, too sterically hindered, right? And DBU as well. So these are strong base but weak nucleophile. Now, my point is nucleophilicity and basicity are totally different property. They don't always go together. All right. How do we know if your reagents are strong base or weak base? Okay. Start off right here. All right, start with the pK. Go back to the chapter 3. Chloride, strong or weak base? Well, look at the conjugate acid, right? Conjugate acid, hydrochloric acid, pKa -7, -8. This guy strong acid. Chloride, totally super stable. This guy dissociate to more stable compound right away. Weak base, all right? Sodium chloride, you eat it, right? Now, opposite direction here. So hydride, weak or strong base? Well, look at its conjugate acid, right? Add proton on that as a conjugate acid. pKa of hydrogen gas is 35. Whoa, that's really weak acid. But that makes hydride a strong base, very strong base. All right, so it go opposite like that. All right, go back to just review real quick. So from a pKa table, strong acid right here. Its conjugate base are weak base. You never use any of this to do elimination reaction. You never ever do this to do elimination reaction. Water sometime, but you have to heat it up. Now you have to spice it up a little, otherwise it won't do anything. All right, come down here. We have a weak acid, so on the right side going to be a stronger bases than at the top. All right. Practically, these are bases that we use in elimination reaction. They are strong base. This is for E2 reaction. This guy right here. All right. Now down here, the acids are really weak. The bases are evils. This guy are evil. The lower you go down, the more difficult to handle. Like for example, sodium hydride, you need to keep it in like with an oil because it reacts with water in the air and you can't use it. It just goes to waste. It reacts with water, become hydrogen gas, and you can't use that anymore. Even go lower, go down to alkane. This guy reacts with everything, even a solvent in the reaction. The solvent have to be really specific for just this guy to be inert for the basicity of what's it called, alkane with a negative charge, basic alkane. Right? But my point is, these are really strong bases down here. Okay, we're gonna use quite a lot of hydride, amide for in the next two chapters. These two, alkene and alkane. With a negative charge, that's in alcohol chapter, in 3 chapters down the road. Okay, these are real strong. Mostly for E2 reaction, we're gonna go to this guy right here, and the hydroxide right there, and hydride. All right. Okay. Identify which of the following reagent would be a strong base or weak base. All right. So we look at the conjugate acid. For example, alcohol right here. What's the conjugate acid? Well, look like that. Look like hydronium ion to me, negative 1.73. I look up the pKa value of the methyl group right here. So negative 2.2. This guy should be close. Totally strong acid, right? So this guy is weak base. All right, sulfide. All right, this one's gonna be a little bit difficult. All right, so look at the structure of its conjugate acid. We don't know the pK of that, but we can compare and contrast, right? Water, pKa about 15.7. Sulfide, look just like water. This is the same group. They do the same thing, right? So two hydrogen is more acidic than water. You know? Hydronium ion is a very strong acid. This guy right here, sulfide with a positive charge, gonna be even stronger acid, right? My point is this guy really strong acid, really strong. So that makes this guy weak base. Okay, it is a weak base. Now, next one, oxide, right? This is ethoxide, right? Ethoxide is conjugate base, it's just ethanol, right? And what's the pK of ethanol? So alcohol is about 16, right? About 16.1, I think. Is it strong acid or weak acid? Oh, that's a really weak acid, like water, 15.7. That's water, basically, weak acid. That makes ethoxide a strong base. Okay. Bromide, all right, bromide. So strong or weak base. Look at its conjugate acid, hydrobromic acid, negative 9. Oh my God, that's one of the strongest acids that we have on the pKa table. So bromide, totally weak, super weak acid. Oh, sorry, super weak base. Down here, lithium hydroxide, all right, lithium hydroxide. So its conjugate acid is just water, 15.7, which is weak acid, right? So its conjugate acid is weak. A base, strong. Hydroxide, you know hydroxide is strong acid. It's a strong base. Okay. Methanol, weak or strong base. Look at its conjugate acid. So conjugate acid looks something like this. Look like hydronium ion. Yeah. So hydronium ion negative 1.73. If you don't, this is what I look up, negative 2.2. But if you don't know, you can compare to the hydronium ion. It looks similar. So oxygen with 3 bonds with the positive charge. All right. So my point is conjugate acid is strong, real strong. Make methanol as a weak base. Okay. Now sodium methoxide, this guy is strong base. All right. But let's say if we don't know, the conjugate acid of methoxide is methanol. Methanol right here, right? Methanol right here. So weak acid that makes sodium methoxide strong base. All right. All right. Last one, DBU. All right. You can look up pK of this guy, pK of conjugate acid of this guy. But let's say what we know about it. So DBU, weak or strong base. We got to look at its conjugate acid, right? So I'm gonna protonate it. There are 2 lone pairs here. One is right here on this nitrogen. The other one is down here. This one is delocalized. You can draw the resonance structure here. Draw down here, double bond go to this nitrogen. All right, so this is delocalized. This lone pair is localized. Localized lone pair is much more reactive than delocalized one. Delocalized chair is already occupied with these 2 nitrogen. This lone pair just stay right there. Localized, really reactive. So take that lone pair, grab the proton transfer. You get an acidic form of it. All right, this is conjugate acid. Now, strong or weak acid though? Can't really tell, but this guy got a resonance structures. Actually, this guy is pretty stable, right? Stable acid, which means a weak acid. Weak acid, right? So because of resonance structure, so stable acid or weak acid. So weak acid, that makes DBU a strong base. Okay? That's how we determine strong or weak acid and base. So nucleophilicity and basicity are totally different things. Oh, halftime. It's a halftime show. Anyway, so I want to say that, summarize the whole thing here. Nucleophilicity and basicity are totally different property. When you consider it, you have to consider it, both of them, all right, separately. You can't just go, strong nucleophile, strong base. Weak nucleophile, weak base. No, they don't go together. Some strong nucleophile, there might be a strong base or weak base. You don't know. All right, or vice versa. All right. All right, halftime show. So a few years ago, you probably have seen the Kansas City Chiefs play San Francisco 49ers, and the Super Bowl halftime show. So we have Shakira, and J-Lo dancing, and become like, oh my God, like a whole talk of the town of this country. My friend told me that when he watched the Super Bowl halftime show, the way they dance are too sexy, and he forgot about the game. Just want to tell you guys. Anyway, so let's moving on.